Okay, welcome to our February 2017 structural modeling project video conference. And we have a number of things to talk about today. We have the agenda up. I think everybody can see that. We started the new Google group, the structural modeling Google groups. Had that for a while. I'm starting to use it more now to focus and collect the information in one place, so it's easier to keep a record of actually what we were doing. I was using a couple different email outlets and interfaces, and that became just a little too difficult to track all the information. So started using this one, the structural modeling, googlegroup.com, and that'll kind of be our official record there. In January, we put out a read-ahead document as a technical report on ResearchGate. And now that's basically the way we're going to do our read-aheads, is to actually create them as a technical report, put them on ResearchGate, get them a digital publication number so people can reference them if they want, make them a little bit more official types of publications. And then we also did the enhanced reachability matrix for the February read ahead. And we hope to bring the size of the documents down, but they seem to be around between 25 and 35 pages right now. So we'll see what we can do with those and try to get them a little shorter. One of the requests we had for a discussion for the agenda this month was to talk a little bit about the existing software, what are the requirements, how you evaluate it, and what you do with it. And so I think the best way to do that is just to kind of talk about the three versions briefly of the software that we have. And the first version is a non-automated algorithm development configuration. And we wrote this software so that we could create a visual display of the algorithm as we were working with it. And all of the logical analysis and all the information gathering and everything is completed by the user. And then the user manually enters that information into the matrix. And the user also manually manipulates the matrix if required. So the second version of the software that we have is semi-automated. And it's similar to the first version of the software, except that the matrix manipulation or the matrix row column swapping function has been automated in that one. And in places where you have a number of row column swaps right in a row within your operations, if you do it manually, you can see how it works, but it gets to be a little onerous to keep doing that. So we automated that specific function in the second version of the software. In the third version of the software, we have a fully automated algorithm implementation. But we've only been able to reproduce in the fully automated algorithm the clustering command that from the interactive handbook. The commands that we've been looking at and trying to come up with the algorithm, and we've so far made some progress, but we haven't completed that. And to make progress on the algorithm development is one of the reasons we kind of circled back and started looking at the matrix operations and the literature in a little bit more detail. and that detail then produced the technical report where we looked at all the different kinds of matrices and kind of did an overview of technical report number 4. And then technical report number 5, what we did there was we looked specifically at the reachability matrix and the issues associated with that, and developed the enhanced reachability matrix that would allow us to encode, created mechanisms to encode information that goes along with these matrices so that you would not lose information. You don't necessarily have to use these, but in cases where you do, where you're concerned about the information loss in the mathematics operations, then you can use this approach. The goal is to have a very clearly defined, well-structured, so it can be automated, and bring that into the future software versions. So with that, I'm going to kind of stop and see if there's any specific areas people would like to talk about.
Well, I'm interested in sort of this step-by-step approach that you're taking, and I would be interested.
Peter, I can barely hear you.
Oh, okay. Gosh. I don't know what to say about that. I'll try again. Is that any better?
Okay. That's better. It's much better.
Okay. What I was saying is I'd be really interested in how to, for example, just with C1, to work with that and just to step through it.
Okay.
Is that going to be available somehow, or could you give me some pointers, or literally just to begin to think about the process by which one would do that, coming at it in the first time, for example?
Yeah, so there's a series of videos and a series of charts that are available online and on YouTube and then on our website. And there's quite a lot of that information. Did it a couple of years ago when we started this. And so if you would like to make a time somewhere, not during this call, but sometime later on, we can get together on the video call and I can walk you through that body of information and where it is and how that works.
Very good. Thank you very much.
Yeah, we have step-by-step instructions on a number of those at the C1 level.
Okay, very good. That'd be a good start.
Okay?
Thank you.
So,
I'll do that.
yeah, when you figure out a time, just let me know and we can just walk through it and do that.
Will do.
Okay. So any other questions? And we got an email from Janet saying that she's having a difficult time getting logged in. So I'm going to send her a couple more invitations. Hopefully she'll be able to join us. Ah, here she is. All right. Hello, Janet.
Let's see. Hi. Yeah, a very odd series of, oh, well. Okay.
That's computers.
Yeah. Okay.
So basically what we've done is we've gone through and talked just a little bit about the our agenda and why we're doing what we're doing, and the 3 versions of the software. And really, the detailed analysis that we're doing in the technical reports now basically have been motivated by some of the issues that we've run across when we were trying to do the automated algorithm approach. We were able to do the clustering algorithm. And for the categories, we were able to do that and reproduce that. The other 2, we've bumped into some issues with, and so we decided the best way to address that was to circle back and really look at the matrix forms and look at the implementations in much more detail.
Right.
And to do the detail, as we looked at, we did an overview in technical report number 4, kind of looked at everything, and then technical report number 5, we did the enhanced reachability matrix so that we could stop the information loss in the mathematics processing if we wanted to, if that was valuable, give us a mechanism to do that. And then we're going to really just look at the other matrix forms in more detail in the upcoming technical reports. So with that, Janet, do you have any questions?
So in today's technical report, you were dealing with variations on reflexivity, but they were all and symmetry, but they were all transitive, right?
Correct.
Okay, just wanted to clarify that. Okay, so are you also going to handle the non-transitive cases similarly?
So that's a very good question. Thomas had the same question, and we're going to. I think there's areas where when you have a mix of intransitive and transitive, which makes them non-transitive. I think there's areas where that might be possible. That would be an advantage to do that, and would be beneficial. And we're going to look at these things. The intransitive one, I'm not quite as I'm not so sure that it will be effective for the techniques that we're using now. The other techniques that we use with symmetry and the large-scale search, the evaluation of system configurations and so forth, then I think the intransitive piece will work there. But due to the fact that we're not focusing on that type of software development right now, we've just kind of put those two on the side and are just kind of looking at the ones where we're doing the logical inference. So,
right. So I guess you could, for an intransitive relationship, a natural language relationship, you could define a related transitive relationship, and then do your manipulations. But I don't know if you can recover. I don't know what that would tell you in terms of your original intransitive relationship. I guess there's probably a straightforward answer to that, but I can't get my brain around it. It doesn't work as nicely as the one you did with the reflexivity.
Yes, so there's a number of interesting patterns that begin to see once you start looking at it at this level of detail.
Right.
And so one of the other lists and other areas that I kind of monitor and think about is an ontology list, and also a Charles Sanders Peirce philosophy list.
Right.
There's people on both of those.
Yeah, we followed those for over a decade. Yeah.
Okay. So
are you talking about Ontolog?
Yeah, Ontolog, and that's one. And then there's a couple others where the folks with the common logic and the mathematicians, basically in the foundations part, they have some discussions. So anyway, so one of the classical relationships that CSP used was gives, right?
Mm-hmm.
And like John Sawyer was just talking about mediation and giving, right?
Mm-hmm.
And he pulled up and talked about a degraded type of mediation with the fact it was left of, is what he was talking about. It was a geometric positioning, but where we have these concepts that when they're transitive, the mediator in that particular case is kind of degenerated. Really, when they're transitive, they have an impact on the ontology.
Mm-hmm.
Where with gives is intransitive, right?
Right.
And so there's a lot of work around that specific relationship, and that actually is the one that, because there's so much work there, that when we go looking at intransitive areas, that's probably the first one to look at. But yeah, it's very interesting, but I'm really trying to balance this to where we can get progress on the software. And what we do in the analysis is really helping us get more definition to the point where we can actually implement it in software.
Right.
So that's kind of where we are there. Yeah, but it's all very interesting. As I said, Thomas had the same questions last week when we were going over this. So yeah. Okay. Anything else? All right. Well, let's go ahead and just pull up the other. I'm going to stop sharing this one, and I'll pull up the report here, which should be this one. I think, here we go. All right. Present to everyone. All right. So it should be the kind of introductory page of the technical report number 5. And just list, well, let's see. Okay, there we go. Just list the 3 areas where we believe there's semantic conflict and issues. And we're really focused on trying to analyze the semantics change between natural language and the mathematical piece. And if there's information loss, how can we basically ameliorate that, or design a system that essentially allows us to manage the information loss. One of the interesting side ideas that popped up into my mind when I was looking at this was the idea of the talking drums in the Congo. There's a fellow that was an expert in the tonal language of the people that used talking drums in the 30s and 40s. And in 1971, he did a Scientific American report. He wrote a book and some other things. But basically, the idea there was that the tonal language itself, the natural language, people speaking to each other, they had more tonal range, and they could encode more information just in the emphasis of their voice than the drums could. But the drums themselves could broadcast the message much further than the human voice. So the benefit for using the drum, of course, was to amplify the message in long distance. But to do that, you had some information loss. And so they used redundancy and in the messages that they sent, and also the people that spoke the drum language had an agreement on certain types of phrases that meant certain things. So there was a standard phrases that went with the drums. And so in my mind, when I was working on this particular problem, it was kind of an analog. We have natural language, and because human capability is limited logically, we need to use computers to amplify our logical and analytical capabilities, but we lose some things by putting it into that form. So we need to figure out ways and mechanisms by which we can actually make up for that information loss. And so the technical report number 5, where we did the enhanced reachability matrix, is our first attempt to build a standard type of process and naming convention by which you can address the information loss. And if that information loss is important, then you can recover the information using these techniques. So that's kind of in a nutshell, what we're trying to do here. make the clear distinction between the mathematical model semantics and the natural language semantics. And then we just run through and detail the analysis for those pieces. So, is there any questions on that part?
Should
I
the-
would, yep.
Go ahead.
I would suggest that you reorder your 3 points there, because the third point about the ambiguity in the mathematical and natural language versions, that is the key issue, and the need to distinguish those and to figure out what you want to do if you lose information by mapping. So I would put that first, and then in particular the reflexive property is what you're focusing on, so that should be second. The lack of constraint on symmetry is, it's not, as you say at the bottom of the page, it's not an issue in the reachability matrix, though it's the key idea in the structural relationship analysis. So I don't know if that, that could be a third point, but the what you have listed there as third is the key motivator of this whole effort. So I just put that first in your listing there.
Oh, okay, those are very good comments. I think that, and looking at it from a different perspective, I can see that makes a lot of sense. And the reason I did it the way I did it was just because symmetry is the key thing for our analytical framework. And so that's the first thing we have to put it into. So, but the order of the issues really is is not meant to mean priority, but if we wanted to prioritize them, then
right. I guess for this particular technical report, there's a focus on the third point, which leads you to address the second point.
Yeah. Okay, I'll definitely. I think what we're going to probably wind up doing is taking and these technical reports after a certain number of them, and then making a larger type of document. So I would expect that in the larger type of document that's based on these, that would be addressed.
So I got
Another way to ameliorate this is to simply list bullets, because there was not really an intention of prioritization.
Yeah, but I still think that what Janet is saying is what she's saying is number 3 is the all-encompassing driving issue. The other 2 things are details.
Oh yeah, no, I agree there.
Yeah, I agree with that.
I have 2 points I'd like to, or 2 questions.
Can you speak up just a little bit?
Yeah, okay. I don't know what's going on there today.
There we go.
Okay. Would it be possible to put an example under each one of those numbers or bullets in terms of, the relation between natural language and the mathematical model? Would that be a possibility? Is that possible?
Well, I think that it's not only possible, I think that's kind of the goal for what we're doing here.
Right.
And so, and in looking at that, so what we have is like the inclusion matrix, the implication matrix, the subordination matrix. We have all of these natural language relationships that were encoded into the mathematics, right?
Right.
And we've run into some areas that seem to be, well, as I said, there's some semantic conflicts and issues. So we started circling back to look at those. And the first one we decided that was necessary to do was the reachability matrix, because it's so fundamental to these other ones. And then in the next technical report, we're going to do one or two more of these types of matrices, and we'll try by March 8 by April to finish them up. I think there's 5 or 6 basic matrices types. And then that's what we will have done. We'll have said, okay, this was the natural language relationship, and this is how it's encoded into the mathematical relation. But yes, that's definitely the goal, to do that.
Okay.
And the more interesting part then, I think, is that these matrix operations, once they're established, then they become core elements in the interpretive structural modeling applications. And there you have even more well-defined natural language semantics. And then the goal then is to say, okay, now we've gone through and looked at these matrices and what they mean. Then we'll go back and up to the next level and look at the those other types of structural modeling applications.
Okay, so that's good. That's helpful, of course. And that sort of, I guess, my second question or point is, this is based in the English language and essentially American English as well.
Right.
How could one take account of, or can one, or is it possible to take account of other languages in this whole endeavor?
Well, it's a really a good question. And so I think there's one of the motivating examples, stories about the application of this, was the government of Mexico used this technique in negotiating with what they called illiterate Aboriginals, right? Of course, the Aboriginals weren't, educated in the dominant culture language, but they were basically literate in their own language. And so what happened with this technique, because of the isomorphism between the structured graphics, the mathematics, and the prose, they found that the structured graphics, what they would do, they would have an event that people get together and talk, and then they would start with the pictures, right? And once they would agree on what the pictures meant, then they would work out in each of the different languages what the prose meant, and then they would do the mathematics calculations and figure out where they were going from there.
Well, that's really interesting. I mean, that would be really good if you could give a reference to that, or if it's just anecdotal, that would be good to just learn about that again some more at some point, because the reason that sort of I'm prompted to ask that question, not only are we doing more work in Europe, but I've just begun reading a book called Don't Sleep, There Are Snakes by Daniel Everett, Life and Language in the Amazonian Jungle.
Uh-huh. Yeah.
And I just think that might have some interesting insights because of the total non-connection with this group before he went there and the way their language evolved. I'm just intrigued about sort of the universals, as it were.
Oh yeah, so to me, the interesting part to me, of course, is in large groups of people that are working on technical systems, whether today they're most always international teams. And I think one thing that Jack has always used to say is, well, the first thing you have to do is language the program. You've got to get people so that they understand what all these terms mean in context. And there's a tremendous amount of work that's been done on, like Common English and a number of other types of forms of communication that can clearly be translated to a large number of other languages. But also, there's also cultural impacts and a number of other things. But when you would go into a team where you had the safety guys, the operations guys, the logistics guys, the cost guys, the chemical guys, all these were like different tribes, right? And they all spoke different languages. And really, you have to sit down and just start using real basic graphics and real basic types of approaches to start getting them focused on what the current specific situation and problem is. And so that's how I see this being able to be used in numbers of places, but even not only over different languages in different countries, but also within, technical groups of people that have, highly refined argot and just all of these different terms. Even though it's the same language, it's completely different concepts.
Oh,
So,
absolutely. Yeah. I mean, obviously that's that's why we're doing it. It's very exciting. And I'm just curious about, how you set the cultural context. And that's a good, good explanation.
well, I think Kevin's the expert there. He's the one that has the expertise in that area. I just have anecdotes. You have any comments on that, Kevin?
I'm wondering, Peter, well, let's take the most common applications of these, of this math in practical applications is the influence relationship and the precedence relationship for planning. And so influence is kind of resource flow, and planning is like a PERT chart. And so what I'm wondering, are you asking, they're both kind of causation? So what I'm wondering is, if you're asking, are there different worldviews on causation in different languages? Is that kind of what you're asking?
I think so. Yeah, different logical structures and different precedences, based on the structuring of the language and the words and their relations.
There's a lot of research into this. There's some. I know there is a multi-volume set on Buddhist logic, I believe, that's available. There are questions of treatment of time in different languages. People have not found any, for all the research that's gone into this, either in linguistics or anthropology, or in AI, or in the semantic web, there have not been any dispositive insights that have changed anything. It's a lot of interesting questions about, how does it affect your use of metaphor if you think of time as the past being in front of you and the future being behind you? Or, I think that's in Australia. There's a case of that. Anyway, so it's a lot of very interesting questions. It doesn't shed any light on what Joe and Mary are doing with the mapping of the English language to the mathematical structures, but it's definitely sort of the broader space that this is operating in, where you would then see, are there any? I don't think there are any blinding revelations that come from other framings where you say, of course, we should all treat it this way. It's just a variety of different root metaphors that are used in different cultures.
Okay, thanks. Yeah.
I'd say that basically there's a couple of interesting points, and one of them is simply about semantics and what things mean in syntax in language. And human language, most all syntax and all meaning and all communication is based on context. And the most interesting fact is that if people share enough context between them, they can communicate using nonsense syllables. And so on the other side, with machine semantics and machine syntax, most all of the meaning and content and state space is based on very specific non-contextual situations. And so there's a strong difference there between the way you determine what something means, whether it's a human or a machine. And in this case, what we're doing is we're just trying to establish a set of isomorphic relationships on some very basic type of operations that are fundamental. And we have the human semantics and we have the machine mathematical semantics. And we're only looking really right now at a couple of different machine semantics. There's others that we'll be using later on when we get into other areas, but it is a very interesting area. And the idea of the Aboriginal people and the indigenous people in Mexico working with pictures, what they're doing there, the groups of people are developing a shared context. And so I really see these processes and mechanisms as a way, as a type of technology and a type of approach that allows individuals that don't have a shared context to actually increase their ability to develop a highly effective shared context fairly quickly. So that's kind of my view of what this is doing. It's actually going to help us as groups of people looking at these things, using these tools to develop a shared context and develop shared understanding.
Yeah, I think that's exactly on point. Actually, once you get to the machine language, you could say there's, once you have translated everything into syntax and constraints, there is no context other than the fact that the machine has been programmed to respond to certain patterns. But and in the controlled natural language, you have an agreement to use. There's the context of agreement to use natural language in certain ways. I guess one could see the ISM process as bringing people from their highly variable languages where they might use nonsense syllables or pictures or whatever to some kind of commonality of language use in the ISM part. And then you want to take them from that into the standardized art relation types. So you're systematically and carefully taking them from very little shared context to some shared context to systematized natural language and then into the machine. So Peter, does that help clarify?
Yeah, no, absolutely. That's all very helpful. I appreciate it. Yeah.
Good.
So yeah, that's kind of the overall goal and what we're looking at here. It's a fairly large space to work in, but we've been making steady progress on it. Things are starting to move forward. So that's kind of where that is. Is there any more questions in this specific area? Okay, I'm going to circle back then to technical report number 4, and we will look at let's see if this is correct. Right. Okay. So we went over a lot of material in technical report number 4, but toward the end, we started looking specifically at our at the matrices that we were working with. Let's see. Well, right. So we had the application structural types that we talked about. Then we had a priority structure, a problematique, enhancement structure, an intent structure, and a curriculum structure. And we classified these basically as compound, as primary types of structural types because they're based mostly on the matrix form. And we had a profile representation and a comparison bar charts. And we said those are primary, but mostly graphic. So then we went through and talked about the what these different structures were, the priority structures and matrices and so forth. And then the mathematics of structure, when we got here, we started then talking about the reachability matrix, which we basically did this month. Now there's, it leaves us with the inclusion matrix, the subordination matrix, the adjacency matrix, and the implication matrix to do, to take a look at. And I'm just wondering if anybody had any strong feelings about which ones we should look at next for the March approach. Okay, so this doesn't seem to be much of a approach there. So I believe what we'll do then is we'll look at the inclusion matrix and the subordination matrix, and the adjacency matrix we'll shoot for March, leaving the implication matrix for April. And it's basically the implication matrix and how you implement that. We bumped up into when we were doing the code from the handbook to actually go through and implement either so it has two different ways you can implement it. It's got a scanning method and a coupling method and a few other things. And it's just not clear that that's what was implemented, or that what's indicated by the outcomes in the handbook. So we just need to go back and look at that. That's really the main motivation for going back and looking at all these in detail.
You know,
these are
Joe,
go ahead.
I mean, they outlined about 60 different typical relations that might get modeled by these matrices, and they named several of them. They named the matrix for the relationship for several of them, right?
Uh-huh.
I mean, why these? I mean, there's 60 others that don't have names where the matrix is not named just because they have a new relationship.
These are the ones out of the literature, out of Mathematics of Structure, and out of the Societal Systems book.
Yeah, but I mean, it's
Well, these are the most foundational. So we'll start with these, and if there's other ones, we can look at those.
no, there's 60 other ones, but they don't have names.
Well,
It's just which
okay.
relationship that you use. I mean, the adjacency if you have an adjacency matrix that has say the greater than, it's measuring greater than or equal to, greater than as a relationship versus is antecedent to as a relationship. We don't have a greater than matrix. We don't have an antecedent matrix. You know, it's just a couple of these relationships. He happened to name matrices for the relationship. I think he was just kind of if this was a pattern to follow, why didn't he name the other 60 matrices?
Well, those are all excellent questions, and I'm not sure why. And the adjacency matrix is a key area of confusion because of the overloading with the mathematical concept of adjacency matrix as opposed to the natural language part. I think in the literature, we see that there's a number of areas, but you're right, the adjacency matrix can represent any relationship that can be represented by a graph, because an adjacency matrix is simply a matrix that represents a graph, a certain kind of graph. And so if you take that point of view, if you take the strict mathematical point of view and say, oh, an adjacency matrix is a matrix that represents any type of graph, then you're right, there's more than 60, there's lots, okay? If you say, well, what's the natural language relationship here that we're talking about? And so we need to actually have this discussion in detail, right? And to go through and look at that. In our work in the AMEI, what we did was we put it together and said, okay, we use connected to, because an adjacency matrix in a mathematical form cannot exist without a graph. The first thing you have to have is a graph, and then you create the matrix based on that graph, and that graph shows the connections. I mean, the matrix shows the connections in the graph. And so we call it connected to, and the 27 buckets, logical buckets in the AMEI, all are based on connected to. So you're absolutely right that there's lots of these, but what we're trying to do now in this analysis is to bring up these points, specifically document them, and address the conflicts between the mathematical semantics and the natural language semantics. So, you know, I agree with you that there's lots of them, and that's the point. That's the point of this whole exercise, is to go through and to document that, point it out, and to say, okay, here's some ways that we will deal with this so that we can maybe eliminate some of this confusion. The whole idea is to eliminate uncertainty and to very clearly define these so we can have a common mapping what they are.
Kevin, do you have a list of 60? I'd be curious to see them.
Yeah,
If you could share that.
I think it actually appears in one of Joe's papers, but I can
Okay.
call
That
one
would be
up.
great. So yeah, you raised the point of, yeah, this seems to be an AMEI exercise of saying, here are the different kinds of the mathematically distinct matrices, and then here are 60 or so different natural language matrices, and what are the mappings between the two sets, and what are the careful mappings to go between them.
Yeah, there's some very interesting things about this, and and so once we go through these in detail, then we can kind of start looking at what they mean. But the original model exchange isomorphism, which was put together by Warfield, was expanded by Sage. He added much more steps and stuff in it. And one of the areas that I believe got confused or made things much more complex than necessary, or obfuscated things, was the interpretation, the application of the adjacency matrix in Sage's work. A key factor, though, a very key factor between Warfield's work and Sage's work on these fundamental matrices is Sage never did an implication matrix. So the implication matrix and the logical implementation is really where we leverage the power of logic to reduce the cost of doing these things. And so the real goal here is to say, okay, let's look at these, let's map them out, kind of see what makes sense, and then let's look at the implication matrix and how is that implemented in detail. So it's there's a lot of interesting things here. So I think, again, let me write that down. I think we're going to try to do the for next, the inclusion matrix, subordination, and adjacency. Shoot for those for April, see how far we can make it. I mean, for March. And then we'll go to the implication matrix for April. Okay. So we have about 9 minutes left. Is there anyone here that any specific things people would like to cover that we haven't talked about yet? Okay. All right then, so I'm going to stop sharing this and reshare the agenda. To be able to present this to everyone. Okay, so let's look. So we talked about those, we talked about these three, and then the future activities. Okay. So the future activities should, so everybody see the future activities there?
Yep.
All right. So basically further develop the concepts of global, local, and relationship precision. So these are, all right, so Thomas is bailing out. Next time he hopes his microphone works, so do I. Local, global, and relationship precision on this particular part. We get into things like the curriculum structure and some of these other more primary types of application structures that are based on the matrices. Then we'll have a chance to specifically address local and global and relationship precision. The relationship precision metric that we're using right now just says if a relationship fits into only one of the AMEI buckets, then it's very, very precise, natural language. And if it fits into all 27 buckets, it's very imprecise. Like connected to is very imprecise because it can fit in any one of the 27 buckets. But the AMEI, one of the advantages and one of its values is be able to say, okay, connected to in this logical bucket only. So we could make it very precise by adding the AMEI name tag to it. And then we also use the AMEI name tags to keep the information in some of the mathematical operations. So we've basically taken a first cut at organizing the application structural types, and we're working on the primary ones right now. And yeah, the mathematical structural types here. So the software commands, the goal now is once we have these things figured out is to basically map the software commands to the structural types. And this is kind of a thing we bumped into when we were working on the software where we really needed to go back and make sure we fully understood what the operations were. And felt we needed to document that in a way that people could read it, understand it, and comment on it. So we could start getting more of a consensus on actually what are the important operations and how should they be implemented in software. Mathematical structural types. And that's something that I think might be interesting, along with Kevin saying there's 60 list of 60 other relationships. Out of those, do we see any other structural types that might obviously be used to support those? And then we're going to be working on the definition of the inclusion matrix, the subordination matrix, adjacency matrix the next month, and then we'll go for the implication matrix for the month after that. And it's, and Peter just needs to send some time when he'd like to get together, and we'll walk through the existing videos and the existing flowcharts and everything, and graphics and presentations that will walk you through how to do, how to work with the first non-automated algorithm development. So we have quite a bit of information about this. It's out there, and you set up a time, and we will walk through that and show you how that works.
Thank you.
All right, so we've got about 3 minutes left.
I have a couple of quick questions. One is, you are still going ahead with Caesar? You're preparing for that?
Yes.
Okay. And the other is, Peter and I saw Len at the IW, and he mentioned working with you. What's the status of that?
Well, you know, Janet, I really don't know. I've made a couple of offers to work with Len, and so far his response has been that he's been busy and he'll get back with me. And so far, as far as I can tell, that interface hasn't been established. So
okay, so it's still aspirational. Okay.
Yeah, so I mean, I'm basically willing to work with him, but I don't. Let's see. It's going to take two of us to work together. Let's put it that way.
That's right. Yes. Yeah. Very good.
All right. So yeah, no, that'll be interesting. You don't know exactly, what's going on there, but we're staying busy doing this. Yeah, Thomas is going to give the paper at CSER. It's going to go down and do that, and it's give him a little bit of an introduction to the community. So
good.
See how it goes.
Mm-hmm.
And it's, of course, on the object metrics.
Right.
Well, anything else?
I guess I could say about Len that Richard Martin and Dick, I can't remember his last name, retired from JPL, Embry, were talking to Len about trying to help him develop a structured database for his isomorphies. And so, we don't know when that will get done, but if they can move that part along, then that would help, bring his project and your project closer together.
Yes. If it's structured into a database, then you definitely have some fundamental logic you can deal with. So we can map that and start going forward. So yeah, it's just, so I said, it's kind of interesting. I've listened to it, looked at it a little bit, but as I said, it takes two to work together. All right. Well, with that, I'm going to basically sign off for February, and we will see you again in March. Everybody take care and have fun.
Thank you.
Very good. Thank you. Bye-bye.
Bye-bye.
Okay, bye-bye.